sklearnpreprocessingKBinsDiscretizer. Description: the KBinsDiscretizer class in scikit-learn is a transformer that converts continuous numerical features into discrete bins. It allows you to create a specified number of bins for each feature, mapping continuous values within each bin to a single integer. This is useful for preparing data for algorithms that are not suitable for continuous data, e.g., decision trees, reducing the impact of outliers, simplifying data for interpretation. Inputs: X, a NumPy array or pandas data frame containing the data to be discretized. Each column represents a feature. Encode string indicating the encoding scheme to use. Options are: one hot encodes each bin, creating a binary feature for each bin in a column. Ordinal encodes bins with consecutive integers. Outputs: transformed X, a NumPy array or pandas data frame containing the discretized data. The shape will depend on the encode parameter. Bin edges: a list of arrays, one for each feature, containing the bin edges. Steps: 1. Binning: the data is divided into a specified number of bins for each feature. The bin edges can be determined automatically using different strategies or provided manually. 2. Encoding: the continuous values within each bin are encoded based on the chosen encode parameter. Metrics: bin width measures the size of each bin. Number of bins represents the total number of bins created for each feature. Visualization plots: histogram: a histogram of the original data can be plotted to visualize the distribution and understand the effectiveness of binning. Heat map: a heat map can be used to visualize the relationship between features after discretization. Fine-tune parameters: nbins: an integer or array like specifying the number of bins for each feature. It can be a single value for equal width bins across features or an array with individual values. For each feature, encode string indicating the encoding scheme. Options are: one hot or ordinal. Strategy string indicating the strategy for binning. Options are: uniform: all bins have equal width. Quantile: bins have the same number of samples. K-means: bins are determined using the K-means algorithm. Uncertainty methods: sensitivity analysis varying the number of bins and binning strategy to assess the impact on pay. Results: challenges and fixes. Challenge 1: choosing the optimal number of bins. Sample use case: discretizing a feature with a highly skewed distribution might lead to uneven bin sizes, impacting the results. Fixes: explore different strategies. Uniform, quantile, K-means and evaluate their performance. Experiment with different bin numbers and visualize the results using histograms to assess pay. Impact on the distribution: consider using domain knowledge or business understanding to guide the bin selection. Challenge 2: choosing the right encoding scheme. Sample use case: choosing one hot encoding when dealing with a high number of bins can lead to high dimensionality and sparse data. Fixes: use ordinal encoding for smaller numbers of bins. Consider using feature selection or dimensionality reduction techniques to handle high dimensionality if one hot encoding is used. Evaluate the impact of encoding on the performance of the downstream model. Challenge 3: handling missing values. Sample use case: missing values in the data can lead to errors or biases in the discretization process. Fixes: impute missing values before applying KBinsDiscretizer. Use the missing values parameter to specify how to handle missing values during binning.